We're back looking now into section 6.4. Now, section 6.4 covers two types of factoring. The first one they call perfect square trinomials. I'm only going to show a couple of those examples because how we factor perfect square trinomials is no different than the factoring work we've done in 6.2 and 6.3. The only characteristic of that is slightly impacted is how we express the final answer. The other type of factoring that I'll look at in a little more detail, but not great detail, will be the difference of perfect squares. The difference of perfect squares is something that basically follows a formula, and if you follow the formula, that type of factoring is not as difficult. It is by far less difficult than the other types of factoring that we've done before. So let's first look at perfect square trinomials. Now, because I have factored and taught the techniques for factoring trinomials in sections 6.2 and 6.3, I'm not going to go through that whole procedure in section 6.4 for this. I will give the factors for the trinomials, but I'm going to go straight from the problem to the factors and talk about how to express the answers. If you need to know more about how to obtain those factors, please refer to sections 6.2 and 6.3. So let's take a look at the first problem they give us. We're going to take a look at question 17. And that's going to be problem t squared plus 6t plus 9. So numbers are relatively small, pretty easy, not bad. When we factor these trinomials, the pair of factors that we're going to come up with this will be t plus 3 times t plus 3. Because 3 times 3 is 9, and 3 plus 3 is equal to 6. However, when we talk about perfect square trinomials, what we're talking about are trinomials whose factors are identical, or whose binomial factors are identical. So we can express these factors as t plus 3 raised to the second. So I've gone through the techniques of how to do this type of factoring, so I'm not here to go through that again. All I want to do is simply give the factors and then express how we can write these factors in a different form in terms of the final answer. So let's just take a look at one other question just to drive this point home. Question 20, we have x squared minus 8x plus 16. So we're looking for two numbers whose product is 16 and whose sum is going to be negative 8. Well, the only two numbers we can do that with are negative 4 and negative 4. Their product is positive 16, their sum is negative 8, but again, I can express this not simply as the quantity of x minus 4 times x minus 4, but as x minus 4 quantity squared. So that is the only difference in the type of work that we have done with perfect square trinomials. It's also worth to note that if you're ever given some expression like this, as x minus 3 squared, particularly when you're doing some type of factoring work like in chapter 7, you can rewrite this as x minus 3 times x minus 3. And it is helpful in the factoring process or the reducing process to do that, as one of those will likely cancel if not both. So that is my coverage of perfect square trinomials. The other major type of factoring that you're expected to know for section 6.4 is what we call the difference of perfect squares. Now, this type of factoring has already been visited in the work we've done in chapter 7, and I've also shown some problems that contain this. So, but we're going to go over the formula on how we get to this. By difference of perfect squares, we have this generic form, a squared minus b squared, where the first term will be a perfect square, the second term will be a perfect square, and we have to have the difference of them. If we have that, then we can write the factors as follows. First, we take a look at what the a squared term is and take its square root. Whatever its square root will be, this will give us the value of a and a. We take a look at the second term in the binomial, which is b squared. We find its square root. whatever its square root is, we will write it as b and b. And then the final part of this formula requires us to write a plus and a minus. Now, it doesn't matter if you write the plus first and the minus second, or the minus first and the plus second. In most cases, it will not. However, sometimes you may have some type of binomial that will result in another binomial here, which can also be written as the difference of perfect squares. And it is easier if you keep the minus term, or the minus sign, in the second binomial, so that if you need to continue factoring, you can do so. We'll take a look at a problem and what that looks like coming up later. So let's start with an example for question 47. This is going to be y squared minus 100. So in this binomial, what we're looking at is the a squared term being equal to y squared. And if a squared is equal to y squared, a is equal to y. For the b term is equal to 100. Or excuse me, not the b term, but the b squared term is equal to 100. So then the value of b, or the square root of b squared, which is b, the square root of 100 will give me 10. So since I have the value of a equaling y, the value of b equaling 10, I write my two binomials as follows. I have y and y, 10 and 10, and again, put the plus and the minus, and we get our binomial factors in this way. Let's take a look at another such problem. Question 48. This is going to be x squared minus 16. Here, we'll just go straight for this without going through the whole formula. The square root of x squared is going to be x. The square root of 16 is going to be 4. And we put a plus and a minus sign there since we have the difference of perfect squares. Okay, let's take a look at some questions that involve a little more work in this perhaps. So this is going to be question 58. In this one we will break down a little more closely. So here we have 9x to the fourth minus 25x squared. So in this question, like I've always encouraged you before, we need first to look for the greatest common factor. And when we look at this, we'll notice that indeed there is a greatest common factor of x squared here. When we factor out x squared, that'll leave us with 9x squared minus 25. So let's take a look now. Let a squared equal 9x squared. That'll give us the value of a being equal to 3 and x. We take the square root of 9 to be 3. We take the square root of x squared to be x. If we let b squared equal 25, then the value of b is going to equal 5. So when we write this in final factor form, we're going to have x squared times 3x, 3x, 5, 5, and then plus minus. So we first factor out the greatest common factor of x squared, and then we take the resulting binomial, 9x squared minus 25, and factor that as the difference of perfect square to come up with the three factors that represent the quantity of 9x to the fourth minus 25x squared in its final factored form. Let's take a look at a few other examples that may be a little tricky, or that may throw some of you for a loop. Take a look at now 61. We have 9a to the fourth minus 25a to the second b to the fourth. So when we look at this question, first thing we want to see if there are any common, greatest common factors. And indeed we have it in the form of a to the second. When we factor out the greatest common factor, that's going to give us 9a squared minus 25b to the fourth. So this is really similar to the last question we just did in 58. The only difference being instead of being 9x squared minus 25, we have 9a squared minus 25b to the fourth. So when we're looking at using the formula for this one, the square root of 9a squared is going to be 3a, and the square root of 25b to the fourth is going to be 5b squared. And again, we put a plus and minus here, and we now have all the factors that make up the factors for 9a to the fourth minus 25a to the second, b to the fourth. One more example to illustrate this for section 6.4, and this is just an example that I'm going to come up with. Kind of a long example, but should drive the point home of why I factor the way I do quite nicely. So I'm going to write very simply x to the 8th minus 256. X to the 8th minus 256. So we're just going to factor this into two binomials. The square root of x to the 8th is x to the 4th times x to the 4th. The square root of 256 is 16 and 16. I write this as plus and minus. So we look at this now and we see we have x to the 4th plus 16 times x to the 4th minus 16. Well, x to the 4th minus 16, this is now the difference of perfect squares also. So we are going to need to factor this further. So I'm going to bring this down because we cannot factor x to the 4th plus 16. They are perfect squares, but it's not the difference. It's the sum, and this is not factorable. X to the 4th minus 16, I can write as a pair of factors. The square root of x to the 4th is x to the 2nd, x to the 2nd, and then the square root of 16 is 4 and 4, and I can write that as plus and minus. So what we have now is x to the 4th plus 16 times x to the 2nd plus 4 times x to the 2nd minus 4. Again, you should notice that x squared minus 4, this is also the difference of perfect squares. So I'm just going to go ahead and write this final pair of factors out. 4x squared, the square root of x and x. For 4, the square root is 2 and 2. We have plus and minus. And again, we're going to bring these down. What we have now for all of our factors, x to the 4th plus 16 times x to the 2nd plus 4 times x plus 2 times x minus 2. And we now have x to the 8th minus 256 shown with all of its factors. Factoring the difference of perfect squares is not a terribly difficult type of factoring, but I do like to throw a few questions that can sometimes look a little out there. Let's look at a few more of those. 64. We have 2a to the 4th minus 32y to the 8th. Now, looking at this, you see the variables are different, so we cannot factor a variable out of this. However, we can factor a 2 out of this. And this will leave us with a to the 4th minus 16y to the 8th. This is going to look similar to this. Let's consider when we try factoring this, what pair of binomial factors we're going to get. The square root of a to the 4th is a to the 2nd. The square root of 16 is 4. And the square root of y to the 8th is y to the 4th. Plus and minus. Can't do anything with this. This is still the difference of perfect squares. So I'm going to go ahead and expand this out. The square root of a squared is a. The square root of 4 is 2. And the square root of y to the 4th is y squared. And again, I'm going to put plus minus here. And now I can write this as 2 times a to the 2nd plus 4y to the 4th times a plus 2y squared times a minus 2y squared. Now, you look at the y squareds and maybe we keep going. However, 2 is not a perfect square. A is not a perfect square. We can stop and we can rest content that this is the answer in its simplest form. If you need to do the work showing A is equal to this, B is equal to that, as we did with our first example, please go ahead and do that. If you want further practice with this in class, we will take a look at this briefly in class also. If you require further practice, please also look online in my math lab for further consideration of this. We're going to take a look now at one other type of question in 68 to see what this is going to look like. We have the quantity of P plus Q squared minus 25. So we have this quantity squared, and then this quantity squared. So for this one, we will go ahead and use A squared equal to the quantity of P plus Q squared. So that will mean that A is going to equal the quantity of P plus Q. For the value of B squared, that's going to equal the value of 25, which will mean that the value of B is going to equal 5. So when we write the binomial factors of this, we'll write these below here. We know writing this here, and I'm bracketing this because we're going to have parentheses in our A value. This is going to be P plus Q, P plus Q. We're going to have 5 for B, 5 for B, and here we're going to have a plus, here we're going to have a minus. So we can write the factors of this as P plus Q plus 5, where this compacts into this, times P plus Q minus 5. Now, this type of factoring is a little obscure. It doesn't come up a lot, but it does come up from time to time. So I'm going to show you one more to reinforce this before we go on to section 6.5. That's going to be the example number 78, and that will be 49 minus the quantity of A plus B to the second. So A, I'll write this to the side here, is going to be 49, or A squared is going to be 49. That will make A equal to 7. B squared is going to equal A plus B squared. And that will make the value of B equal to the quantity of A plus B. For the purpose of factoring, it's important to retain parentheses for the reason that will show up in a moment. So we're going to put brackets here. So for the first part, we have 7 for A and 7. For B, we have A plus B and A plus B. But remember, we have to put in our plus, and the real kicker, we need to put in our minus. If you're looking at some multiple choice test, you may not see it this way. You'll more likely see it where it's going to be simplified. Plus sign, not a big deal. They'll probably have 7 plus A plus B. But for the second one, where we have a minus on the outside of the parenthesis, the negative sign has to be distributed across the A and the B, giving us 7 minus A minus B, and giving us the pair of factors for this above, which represents the difference of perfect squares. That concludes our review of perfect square trinomials and the difference of perfect squares. We will pick up in section 6.5 next, where we will cover the sum and difference of perfect cubes.